Welcome back from the break. Thank you for joining us on the first day of this Policy and Practice Forum. Next up on today's agenda is the panel presentations. My name is Robert Thompson, and I will be your moderator for this portion of the forum. A little bit about myself. For the past 14 years, I've worked as a senior forensic science research manager with the Special Programs Office for Forensic Sciences at NIST. Prior to this role, I worked as a forensic examiner with the ATF, the Washoe County Sheriff's Department, the Oregon State Police, and the Genelex Corporation. I also hold a Master's of Forensic Science degree from the George Washington University. I am a court-qualified expert in several disciplines and have testified in numerous federal and state courts, and I have several publications in international forensic science journals. We have 3 panel presentations for you today. As you watch the presentations, please type any questions you have in the chat. We'll get your questions answered during the Q&A session after all the presentations. Our first presenter is Thomas Brian Renegar. He goes by Brian. He will discuss the application of 3D microscopes to firearm and toolmark examination. Brian currently works as a physical scientist in the Physical Measurement Laboratory at NIST. Brian has performed scan, probe, and optical 3D measurements and calibrations in the field of surface metrology for over 25 years. He is also heavily involved in research of measurement methods for forensic ballistic identifications of firearms and toolmarks. Brian currently serves as chair of the American Society of Mechanical Engineers B46 Committee on the Classification and Designation of Surface Qualities. He is a technical advisor to the Association of Firearm and Toolmark Examiners and a member of the Technical Working Group for 3D Toolmark Technologies. Welcome, Brian.
Hi, good afternoon. My name is Thomas Brian Renegar. I work at the National Institute of Standards and Technology. Today I'm going to talk about 3D microscopes and their application to firearm and toolmark examination. First, a quick disclaimer that some commercial equipment may be identified in this presentation, but this identification is not intended or implied as a recommendation or endorsement by the National Institute of Standards and Technology. Here's an outline of the talk. So I'll start with some background information, talk about some 2D microscopy and compare and contrast them to 3D microscopes, and go through some basics of 3D microscopes and how they function. And then I'll go into a little bit more detail on a few of the different kinds of microscopes that you may see in the forensic lab: confocal, focus variation, interferometric, and photometric stereo. Then I'll talk a little bit about some different considerations about measurements, range versus resolution, and measurement stitching. And then discuss a little bit about calibration and quality control and how that relates to some documentary standards and some of the organizations. So first, a little introduction about 2D microscopes. Well, these are have been used for many, many years in the forensic laboratory. Comparison microscopes are kind of the workhorse of the lab. So everyone, I'm sure, is familiar with those. There's all kinds of other kinds of 2D microscopes as well, though. There are stereoscopes, and there are also microscopes that are attached to searchable databases. So this allows for the rapid search of images from hundreds, if not thousands, of other images. So for 3D microscopes, there's many kinds as well. And these are only some of the variations that are available. So focus variation, interferometry, confocal, and photometric stereo. These are some of the kinds that you may see in the laboratory. And each one of these also has some subset variations and differences in the technology that's being used. So I'll try to cover some of the main styles that are being used today. First, I wanted to give a little compare and contrast between 2D microscopes and 3D microscopes. And so at the top there, you see image intensity as a function of X, Y is not equal to topography or Z height as a function of X, Y. And that's because they operate in very different manners. So a 2D microscope, you're looking at basically a representation of the surface itself. And the representation is dependent on many factors of the microscope and the surface that you're looking at. So there are considerations of slope angle, shadowing. You can have multiple reflections. There can also be different optical properties from the different materials, which you can see in this image here. So these are two different materials and they reflect the light differently. And one of the big factors here is the illumination direction. And so that plays a big role in determining what the image looks like and how it represents the actual 3D surface topography. 3D microscopes, on the other hand, measure the surface directly, and so they don't have the same kind of issues. In most cases, these are very controlled illumination settings. You know, the illumination is within the microscope itself and is controlled and calibrated. And so you don't have the same kind of issues that you have with 2D microscopes. So the takeaway here is that with 2D microscopes, they're highly sensitive to lighting conditions. Okay, so as an example, here are two images of an aperture shear from a breech face image. And at first glance, you may think that these two images are from different samples. But actually, these two images are from the exact same sample, and they were taken within several minutes of each other. The reason they don't look similar is that the lighting conditions have been changed. So the image on the left here, the illumination was from the 12 o'clock position, and the image on the right, the illumination was from the 6 o'clock position. And because of the change in illumination, the image representation of the surface is different. So this right image is actually an animation. It's a series of images, and what's going to happen, I'll show the video here. What's going to happen is the illumination is going to change from the 6 o'clock position to the 12 o'clock position. And as that changes, you'll see how the representation of the striations will change. So here you can see the illumination is changing angle. And as it comes around to the 12 o'clock position now, you see that this aperture shear is in fact the exact same sample. Let me run it one more time just so you can see that. Okay, so as you can see here, one of the disadvantages of 2D microscopy is that the lighting angle is critical for repeatability. So this slide here shows some benefits and disadvantages of 2D microscopes and 3D microscopes. And so that's one of the big ones, is the lighting angle has to be consistent to get repeatable images so that you can compare images from different instruments and from different operators. As I mentioned, it does not give a direct measurement of the surface topography, so that's another disadvantage. Of course, 2D microscopes are quick to learn, easy to use, and they do have very fast acquisition speed, so those are definitely benefits to 2D microscopes. In comparison, 3D microscopes, they do actually measure the surface topography instead of the intensity as a function of X, Y. They're looking at the surface topography. And they're not sensitive to lighting conditions because these are generally controlled. The lighting is contained within the microscopes. They are calibrated with the lighting angles where they are. So this is not an issue for them. And they facilitate objective comparisons. But there are some disadvantages, of course. They can't resolve high slope angles in some situations. They're definitely more time consuming to take measurements of surfaces. And they can also have signal to noise issues or data dropouts, depending on many factors, the objectives being used or the specific 3D microscope being used. So the takeaway here, this is why many people have been pushing for 3D microscopes in the forensic lab, is that they are measuring, they are giving you the surface topography, they're not sensitive to the lighting conditions, and they facilitate objective comparisons. So I'll go into a little bit of detail. I think it's important in the context to understand how some of these microscopes operate. I'll try not to get too much into the weeds, but in order to fully understand how the systems operate and maybe to do troubleshooting, if something's not working right, it's important to understand at least the basics and the concepts of how some of these microscopes work. And the four that I have here, you can kind of categorize them into two areas. So the confocal, the focus variation, and the interferometric are what we call scanning microscopes. That is where they scan either the sample or the objective relative to each other through the focal plane and take a series of images as they are scanning through. And this could be hundreds of images or it could be thousands of images, similar to image stacking. Okay, so all of this information is saved, and then the data is analyzed using a computer, and the surface topography is able to be calculated through this information. With photometric stereo, it works a little bit differently using sequential illumination. So here it uses multiple light sources that are positioned in different locations around the sample, and sequential images are taken while these light sources are turned on and off. And then once this series of images are captured, then that information can be used to reconstruct the 3D surface topography. So I'll show a little bit more detail about one of these microscopes and then more of an overview of some of the other ones. So confocal microscopy, this is kind of a schematic of the optical system in the microscope. And so you have a light source here, here's the sample, and here is the detector. This has a series of pinhole apertures, and what that does is it rejects illumination that is not in focus. So any of the out of focus surface, all those light rays are blocked by the pinhole aperture, and only the in focus information is returned to the detector. And that information is used to calculate the surface topography. So this is a video of what actually happens during a scan using a confocal microscope. So let's say we're looking at the top of a sphere, okay? And as we are scanning the microscope down through the focal range of the surface, we have a dark image except for the light area here, which represents the focal range as the microscope is scanning downward. So again, all this information is collected as a stack of images. And then when we look through the stack at, say, one point on the surface, you get an intensity curve here. And the peak of the intensity corresponds to the Z height or Z position of the surface at that point. So you can see for different points on the surface, that intensity comes in at a different Z position. And using all this information, then we're able to back out the entire surface and generate 3D topography. So two of the other techniques that use this scanning approach are the focus variation and the interferometry, which is coherence scanning interferometry, also known as CSI interferometry. So for focus variation, this is more of a standard bright field optical system where the object is again scanned through focus and an image stack is obtained. And this uses a best focus or best sharpness approach using the highest contrast of the pixels. So it looks at the surrounding pixels and determines where the highest contrast or best sharpness is found. And that's done for each point on the surface, generating the 3D topography. With the interferometer, it uses a design that splits the light into two paths. One is an object path, which is here, and then one is a reference path, which is here. And when the light recombines at this partial mirror, it produces a series of fringes, which you can see across the surface here. So these are light and dark bands that are produced by the interference. So that information is recorded as the object is scanned through focus, and then the fringe envelope is used in calculating the z-height position of each point on the surface. For photometric stereo, as I said, this uses a set of light sources that surrounds the sample. So you can see this animation here showing what it might look like as it's moving around this pyramid structure. And so the system sequentially takes images with all the lights, turning on and off. And then the computer captures all this information, and it is able to obtain the surface normals of each point on the surface. And then from that, it's able to reconstruct the entire surface. I do want to point out that my example before with the 2D microscope and the light source being from different orientations, that's generally not a problem for these kinds of instruments, because for the very important point that each light source relative to the camera and sample is precisely measured and or calibrated. So that's critical to the function of this kind of microscope, is that the position of each one of these light sources is known very precisely, and it's calibrated, and it uses that information to obtain the 3D surface topography. Okay, so some considerations to think about, and this applies to both 2D or 3D microscopes, is range versus resolution. So resolution, of course, is important. We need to make sure that the samples that we're measuring have high resolution, that you're able to see the structures and the striations that are important. And that's oftentimes limited by the pixel size of the detector or by the optical components in the microscope itself. So one of the ways, of course, that you can get higher resolution is by using multiple objectives. So you can use a higher power objective if you need higher resolution, but the trade-off, of course, is that that limits the field of view size or the lateral range that you can see. So as an example here, maybe we're looking at this breech face impression at 5x objective. Maybe we want to have a little bit higher resolution, so we can switch to a 10x, and that'll give us a little better resolution, but now it limits our field size. If we go to a 20x, we'll get even higher resolution, but now the field size is even smaller. So now, as you can see, all we can see is the firing pin impression instead of any of the breech face. So one of the ways around this is to do measurement stitching. So this is a process where multiple images are recorded of the sample at higher magnification. So you can see this grid pattern on this head stamp here. So we can measure this multiple times as we're scanning laterally across the sample surface. And this time lapse here is showing what that looks like. So measuring the top surface of this cartridge casing over many fields of view, but at higher resolution. And then this information can be stored and then combined. Kind of what that looks like is here. So you have lots of pieces, lots of measurements of a large image, large surface, and these can be combined together into one image. And in practice, how this works is there's actually overlap area between adjacent images, and the overlap area is used to register the images relative to each other. So they are registered laterally in X and Y, And they'll also be registered vertically to make sure that all of the surfaces are measured at the exact same height. And once all that is done, then they can be combined or merged into one image. So this gives you high resolution while also still maintaining large lateral measurement ranges. The downside to this, of course, is that it takes more time. And there's not really too much way around that. Obviously, if you're taking, in this case, 16 images, it could take potentially 16 times as long as one image. But this is one method of giving higher resolution if it's needed. One of the things to look for, though, when doing measurement stitching is it's important to look to make sure that this stitching operation has performed properly. And so in this case here, you can see this breech face measurement has something funny going on here. There's some lines and some strange artifacts of some sort. And those actually are right where the stitch lines were. So in this particular measurement, the stitching operation did not do a perfect job in stitching the individual images together. There's still a residual, maybe there's a Z height difference between these areas. I'm not exactly sure what happened in this case. And it doesn't happen too often, but it's something to keep note of and to just watch for when you're doing stitching. So that gets us to calibration and quality control. Of course, 3D microscopes have to be calibrated. This ensures accuracy of measurement results within given uncertainty estimates. And it's a critical part of making sure that the measurements are precise and that they can be compared to other microscopes, to other instruments, or to other laboratories. We have to make sure that we're all speaking essentially the same language. So in this case here, we're talking about metrological traceability to the SI unit of length. So that is the metric system, and the SI unit of length is the meter, or smaller components of that are, of course, the millimeter or the micrometer. And so to calibrate the instrument helps to ensure that we can compare measurements between laboratories, which is very important when you're doing examinations, and you may have to compare some images that were taken from one laboratory to another laboratory, or even within the laboratory, there could be multiple images or instruments that are taking measurements. And so these all have to be calibrated so that we can compare measurements between all of them. So what needs to be calibrated? Well, there's a lot of things that could be or can be calibrated or checked, verified, and some of these are more important than other things. For instance, the vertical scale amplification factor and the lateral scale amplification factor. These are very important aspects that need to be calibrated and verified and checked. There's a number of other things that can be checked, like the linearity, instrument noise, flatness errors, lateral resolution, all kinds of things. And this is not an inclusive list, and it can vary depending on the kind of instruments you're using. So depending on the type of instrument, there may have additional calibrations that are necessary, or maybe because of the style of the instrument and the way that it works, maybe some of these are not necessary. It really depends. And unfortunately, that means that it may not be a one-size-fits-all solution, that it may greatly depend on the type of instruments that are being used. It can also depend on the laboratory itself, how many measurements are being done, how often they're done, or how many different kinds of instruments are being used. All these factors play into what needs to be calibrated and the frequency at which it needs to be calibrated. So that gets us into quality control, which means that you need to ensure measurements are consistent over time. And that's the repeatability, reproducibility of measurements. And this can be affected by many things. Time is one, environmental conditions as well. operators, or even instruments. Instruments go bad over time, occasionally, and so that you could have an instrument that has an issue. You could have multiple instruments. There could be all kinds of factors. So it's important to make sure that the measurements that you're taking over time are consistent. And so control charts, that's a good way of doing this. So this is a key diagnostic tool in demonstrating quality control and ensuring measurement results are within specified tolerance. So this is just an example here, some measurements that were made, and you're looking at kind of the day-to-day variation of this particular sample that was measured on an instrument. And you can see how it's fluctuating up and down. And this is typical, to see repeatability measurements similar to this. But the important thing is that they are falling within the upper and the lower control limits. So that ensures that the measurements that we're doing are consistent and that we can trust these measurements. Now, if something were to happen and one of these values went outside of the control limits, that would be a reason to pause, to stop, and to see what's going on. That maybe there was a bad calibration that day, maybe the instrument is bad, any number of factors. But this ensures that the measurements are consistent over time. So what needs to be calibrated or checked? Well, as I mentioned, this is maybe not a one-size-fits-all, and this is still being considered by a number of organizations. So the Organization of Scientific Area Committees, or OSAC, this is a large organization with many forensic examiners, practitioners that are developing documentary standards. And these are helping to define minimum requirements, best practices, and standard protocols and other guidance to help the forensic laboratory. Another organization here called the Technical Working Group on 3D Toolmark Technologies. They are working as well to provide guidance and recommendations to the Firearms and Toolmark community in instrument assessment and virtual comparison microscopy. So there may not be a one-size-fits-all answer to what exactly needs to be calibrated, what needs to be checked, what control charts need to be in place. And essentially, it's going to come down to each individual laboratory that they need to make some of these decisions. But these organizations are going to help provide a lot of guidance and help with the 3D microscope validation, and hopefully make it a little bit easier for the laboratories themselves in determining what exactly needs to be done. There's also some documentary standards on the hardware itself, so the 3D microscopes. So the ISO, or International Organization for Standardization, they have a suite of documents. These 25178 documents are on 3D optical hardware. And so this is included as a reference. So these are additional documents that could be reviewed if you are interested in more information about how 3D microscopes work. Part 600 here is more general information, metrological characteristics for aerial topography measuring methods. Part 604 pertains to coherent scanning interferometry. Part 606 is focus variation microscopy, and part 607 is confocal microscopy. So these standards are available to review if you're interested in more information. Well, that's it. Thank you for your time.
Thanks, Brian, for your presentation. As a reminder, if you have any questions for Brian, please type them in the chat and we will get to them during the Q&A session. Our next presenter is Todd Weller, who worked as a criminalist since 2000. Todd's presentation will examine virtual comparison microscopy and discuss its potential to enhance the quality and accuracy of firearm and toolmark examinations. Todd worked for the Oakland Police Department for 16 years and is now in private practice. He has performed casework in drug analysis, DNA analysis, and crime scene investigation. Since 2008, he has primarily worked in the firearms identification specialty and graduated from the National Firearms Examiner Academy in 2009. Todd has a Bachelor of Arts in Biochemistry and Molecular Biology from Dartmouth College, as well as a Master of Science in Forensic Science from the University of California, Davis. For his master's thesis, Todd collaborated with NIST to study confocal microscopy on test fires from consecutively manufactured firearms. Todd is certified by the American Board of Criminalistics, and he has served as the president of the California Association of Criminalists. Todd previously served as the chair and is currently the vice chair of OSAC's Subcommittee on Firearms and Toolmarks. Thanks for joining us today, Todd.
Thank you for the introduction. Again, my name is Todd, and it's my pleasure to talk to you today about the software involved in what we're now being called virtual comparison technology, provide you a very brief and kind of very high-level overview of some of this technology. So before I begin, I want to give a brief disclaimer. I'm going to be showing examples of hardware, equipment, and software, and these are being only used for demonstrative purposes and are not any endorsement or promotion of a particular company or product. So what is virtual comparisons, or virtual comparison microscopy, or VCM for short? Perhaps when I say virtual, many of us imagine something like virtual reality, where you put on some goggles and you can view a video game or video in 3D reality, essentially, but it's virtual because it's been digitized. Or maybe perhaps you have a little more of a dystopian view and you think of something like the Matrix, where your brain is plugged into some virtual world, and it's virtual because it's not real, it's just a digital representation. Well, let me assure you that neither of these are what I intend or what the profession intends when we talk about virtual comparisons. I think a place really to begin is to compare what virtual microscopy is to the traditional method, or the method that's used in day-to-day casework today, and that's light comparison microscopy, or LCM. So LCM has been in use in firearm forensics and firearm toolmark comparisons since the early 20th century. Over 100 years ago, this technique was first applied to fired ammunition components. And while the technique has been the same, certainly the technology and the equipment has changed and improved, both in optics and certainly the ergonomics of the equipment. Specifically, the equipment is what's called the comparison microscope. And the way a comparison microscope works is you can mount two separate objects underneath two microscopes, and then light is shown on those, and those light sources can be manipulated and moved to adjust the lighting and illuminate different surfaces of interest. And the image is then projected up or reflected up into the microscope, and the two microscope images are combined using a series of prisms and mirrors, and then combined into a single image that's viewed through the eyepieces of the microscope. And often a digital camera is also attached nowadays so that a digital picture can be seen of what's underneath the microscope. That digital picture looks something like this. Here we have two objects mounted, and on the left is one bullet. On the right is a second separate bullet. And down the middle here, we have a dividing line, sometimes called the prism line, that divides the two objects. And so this instrument, the comparison microscope, allows a forensic scientist to compare two objects. Here we have two bullets, but we can look at two fired cartridge cases or other tool marked items and look for similarities or dissimilarities of the tool marks, those microscopic tool marks that are not visible to the naked eye and require magnification to see. And then we can compare those two different surfaces side by side. Even further illustrate how this is used in day-to-day casework, here's an example based on my own experience of how light comparison microscopy, or LCM, the workflow goes. So first you take the two objects that you'd like to compare, and you place them under the microscope and begin your visual comparison. And then if you see something of interest that you want to further document, you can document that area with a photograph like I just showed on that prior slide. So this is photographs taken using some sort of capture software on a separate computer that's not integral to the microscope itself. You then will typically take that photograph and annotate it somewhat. I will use a separate software program to do this. Sometimes you can use the capture software, but it's not unusual to use a separate annotation software. And what are you annotating? Things like the magnification, your own initials, the item numbers, maybe even annotating different features depicted to really highlight the areas that you're using for a decision. Once you're done with that image, then you need to incorporate it into your notes somehow. So another program is open, something like Microsoft Word, where you import that image and then write some narrative notes to describe what the significance of that photograph is. So after you've gone through these different steps and these different software programs, you've now documented that one comparison. You then can move on to another comparison by selecting your other items, and you go back to square one. So not only is the comparison microscope useful, but also often a chair with a swivel and one that has caster wheels is a very useful tool in the trade as you're moving back and forth between computer and microscope and working through this workflow. Okay, so there's kind of a very brief background of light comparison microscopy. So what is VCM? Here's one of the earlier papers that I'm aware of that first described this technique, and they have a useful figure in this paper by Senin. And it's really broken into two components. So first, there's the acquisition hardware. And in other talks, we're going to hear a lot about the work that goes into the validation and the quality assurance of these, and even the different manufacturers of these. I'm not going to talk about that, but let it be known that in order to get to this software, you need some sort of acquisition system to measure the physical specimen. So you place the physical specimen, whether here we have a fired cartridge case or a bullet, and then this hardware can measure the microscopic surface. And once we measure it, we can save those measurements, and if we can turn it into a 3D representation of that surface, of the physical specimen. And then once we have that 3D surface, we can then put it into our analysis software station and move on to the virtual comparison world. As another visual example of what this looks like, on the left here, we have a traditional microscope image. And then if we digitize that, create a virtual image, we can now view the same surface features, but instead on the computer screen versus through the oculars of a comparison microscope. So what are some different uses of VCM? I'm going to go through a couple examples, and these are just a few examples. There are other uses as well as possible, but one is obvious, that is the digital comparison and the kind of instant archival of the evidence using digital data. Another is to use these files and this comparison software to conduct research in the form of error rate studies and validation studies. I'll show an example of that. And then looking towards the future, of course, if we have digital files, we can start getting computer comparison algorithms involved. And while I don't think that's coming tomorrow, it's certainly something where the field is trying to go. And I'll give an example of a workflow that I think might be coming down the line sometime in the future. So that's where we'll end our talk. So first, let's go into the comparing and archival evidence. An example from a year ago is from the scientists at the National Institute of Standards and Technology at NIST, and they were provided access by the National Archives to the physical specimens, the physical bullets and bullet fragments involved in the JFK assassination. And the NIST scientists painstakingly and meticulously performed the measurements using that acquisition hardware of the physical specimens from the JFK assassination, stitched a number of samples together, a lot of hard work to do this. And at the end of the day, you can now go to the National Archive and download the digital files that they collected. So now, regardless of wherever you are in the world, you can download these samples and using open source software, virtually view the physical evidence from the National Archives. So one example of the archival and preservation of evidence using this very, very, very famous crime. In day-to-day casework, how could this potentially work? Let me take you through a theoretical example that's not far-fetched. So for example, we have evidence from a crime, and let's say this crime occurs today, and we are using our archival hardware to create a 3D representation. Then imagine 6 months from now or a year from now, a second crime occurs, and we have reason to believe that the same firearm was used between these two incidents. Traditionally, comparisons are performed using the physical specimens. And so in order to perform a comparison of the evidence between crime number 1 and crime number 2, we would have to go back to the submitting agency and recall that physical evidence. Sometimes this is not necessarily a trivial task. That submitting agency may have to mail evidence because they're hundreds, maybe 1,000 miles away. They're all the way across the country. But rather than, if we're using this technology, in order to comparison, the retrieval of the evidence to perform the comparison, since it's been digitized, can be near instantaneous. And so the comparison and the confirmation and verification can all be done on the computer when the examiner is ready to do so, and not being held up by retrieval of the physical evidence. So no longer does time and space or distance now prevent a comparison from moving forward. What does this comparison software actually look like or function? Well, I've created a little video here. There's a number of controls here that I won't show them all here, but you can see along the top there's a tray of physical specimens that have been measured and digitized, and those can be pulled into the comparison screen here. And you can see the comparison screen looks much like that comparison photograph that I showed, where we have 2 specimens. And then the light source can be moved. This is a virtual light source, but it can move just like it would be on a microscope. And then the physical specimens can also, or now here we have the virtual specimens, can be moved independent from each other, rotated and translated, and the microscopic tool marks can then be compared. So here I've moved the items, I see some correspondence, and just like a microscope, I also can zoom in to better compare those features, see if there's agreement. And the dividing line can also be moved as another visual aid for the comparison, and most comparison microscopes can also do that. The last part of the software that differentiates it very much from a light microscope is the ability to take notes within the software. So you saw I opened that tab there, and in this tab is the ability to record narrative notes as I'm performing comparison. One of the really advantages using software packages is it has the ability to automatically tie the notes that I'm taking to the items that are on screen. So any forensic scientist, whether it's in Firearm Toolmarks or forensic biology, learns very early on that keeping track of which item you're looking at is critically important. I mean, it's fairly obvious and straightforward. But here, that critical key, that critical component of keeping track of items is being done by the software, because this is tied, these item numbers are tied to the images you're looking at. So this is ability for the software to improve examiner quality and accuracy. And I'm no longer now having to take notes in a separate program. It's being done in the software right there next to the visual comparison that's on screen. So another feature that software potentially has is to annotate the images and to highlight areas with that may be of interest. So much like you would do in, say, Photoshop, you can create, the software creates a layer, and then I can highlight areas that I have of interest. So here I've lined up these striated marks on these 2 fired cartridge cases, and then I'm highlighting them to signify that I find this area of, there is significant agreement there to support a decision of same source. And now that I've painted that annotation on there, it's linked to those 2 items and the areas that I painted. So this is a way for perhaps, say, a technical reviewer can come in and check my work and see, have I documented the work, and do my observations in the areas that I'm highlighting support my ultimate conclusion. So a reminder of that example light comparison microscopy, where we're going back and forth between computer and microscope, as well as opening a number of software packages. Potential virtual comparison workflow is to simplify things, where all the comparisons, the annotations, and the note-taking is all being done in the same space on the same computer screen. Now I said potential workflow because your mileage may vary depending on a laboratory's their own workflow of the light comparison microscopy, as well as the software that is used for the virtual comparisons, whether or not it has some of these features that I've discussed. The point here is to show the potential and why there is interest in this type of software. Okay, so I've talked about laboratory comparisons and operations. Let's talk a little bit about some of the research that this technology has also been used on. So here's 2 more citations. I'm a co-author on both of these. And here we're using that software that I just showed to actually test examiner performance, also called error rate studies or validation studies. As one example of an advantage of using virtual samples for these types of studies is to again compare it with the physical example. One of the probably most famous and well-conducted studies is the Baldwin study. And so this is a much cited and referenced firearms examiner error rate study that used light comparison microscopy, and they sent out physical specimens. They sent out fired cartridge cases. So in the final study, there are 218 participants, and there are 15 test sets and 4 specimens per test set. So if you quickly do the math, that's over 13,000 physical specimens sent out to the participants. And actually, if you read the manuscript, the authors of this actually collected approximately 20,000 physical specimens, because not everyone who received a test package mailed something back. But that's, you can imagine collecting 20,000 test fires and keeping track of them, labeling them, packaging them, shipping them is just a large task to get an error rate study like this off the ground and running. So that's a really large undertaking. So to contrast that with the Chapnick study, which we conducted, this initial barrier is essentially negated. So in our study, we had 40 test sets and 3 specimens per test set. That's only 120 physical specimens. And since we're digitizing them, the number of participants is essentially meaningless, because once it's digitized, it can be sent out via the internet, and copies are just provided and downloaded to each of the participants. So another area of interest when we were studying examiner error rates was we asked the question, we're wondering, is there examiner consensus with the areas being used and the amount of areas being used by examiners when they're reaching a decision? And I'll show some examples from the Chapnick paper here. So how did we do this? Well, we used those annotations that I showed earlier. And as a reminder, this is what the annotations look like. So in software, you can paint or highlight areas either of similarity or difference. And we asked examiners to do this for each comparison they performed between a known and an unknown. Then what we did with those annotations was we took each individual independent annotation, and then we combined them all into a overall annotation heat map. And heat map meaning the hotter or closer to red in the spectrum, the more consensus there is with that surface that's being used. And so we were wondering, would we see in our study examples like this where there's agreement amongst the majority of the test takers that of the amount of area to be used for, say, same source decision, an identification decision, and elimination decisions? So here's one figure from the Chapnick study. And you can see when we saw this time and again, where there's just a smaller surface area that most of the examiners are using, and not the entire surface itself, but there were highlighted areas where there is consensus on what marks examiners are using for the decision. One of the reported conclusions was that the annotated maps provided insights into both individual and overall examiner decision-making processes. Examiners had a high amount of agreement with regard to the areas useful for identification and elimination, as well as those areas which should be avoided for definitive source attribution. So here the software really provided some insight into the examiner decision process, that not something that I think could be studied prior to the use of this technology. The annotations also provide insight into error. And let me show you an example, again, from the Chapnik study. So the way the test design overall worked was each examiner were provided a number of test sets. So in one test set, they were given 2 knowns. And so the 2 knowns, meaning you can take it for ground truth that these 2 samples are from the same firearm. And then they're given an unknown and asked the question, is this unknown fired in the same firearm as the 2 knowns? So if it is, they would report identification. If it's not, they would report elimination. So in this case, we had the 2 knowns and unknown, and the ground truth is that these 3 were all fired in the same firearm. But as you can see by the title, this was in a false elimination. So one of the test takers was a trainee, and they reported elimination, despite the ground truth being same source for all 3 of these. And so do the annotations provide any insight into why this trainee reached this elimination decision? Well, in this case, they did. So here we have the trainee's annotations. Now, this is not the heat map annotation, which is the consensus that I showed before. This is just one person's annotations. The red representing an area that the trainee is highlighting as being significantly different, and blue where the trainee sees similarities. And so since the trainee reported elimination, it's a reasonable conclusion that this individual thought that this was a sufficient grounds for elimination. And this really provides a critical or useful training ability here, because not only do we know this trainee falsely eliminated, but now we know the features that they're using, and the trainee can learn that this type of difference is not a reliable difference for reaching an elimination decision. So let's move to the future, and that is comparison algorithms. So up to this point, I've only talked about using the comparison software to essentially supplement light comparison microscope or to essentially serve the same role as the light comparison microscope. But if we have items digitized, we can get comparison algorithms or computers involved. And that can be a little bit of a scary, daunting task. Algorithms can kind of sort of be a black box, and it's tough to understand sometimes what they're doing. I don't think that should be a hurdle, though, or prevention from moving forward. I think one potential use is the concept called computer-aided verifications. And ultimately, the goal is some sort of statistical score of surface similarity, something like a likelihood ratio. I'm not going to talk about that second option, but I do want to provide an example of the workflow of how I think a computer-aided verification might work. If you're interested in more discussion about the implementation of these algorithms, I think this is a nice discussion by Swafford and Champaud about algorithm implementation in pattern evidence. And they provide a roadmap on potentially how to adopt that. And in this paper, they have 6 levels of algorithm implementation, anywhere from 0 to 5, 0 being there's no algorithm at all, and 5 meaning the algorithm is doing everything. Imagine a self-driving car. Certainly, I can see 1 being implemented, and an example might be you using the algorithm to align the samples, but then the examiner uses that alignment, see if they agree with it. This is just to kind of speed up the process. I also think level 2, where the examiner reaches their own opinion, and then the algorithm is used as the quality control measure, has potential, hopefully in the near future. So how would that workflow work? Could go something like this, where you have your evidence, the examiner and the algorithm work separate from one another, and they each reach their own decisions. So say, for example, here, the examiner reaches the same source conclusion, and the algorithm provides some sort of confidence score that supports that same source conclusion. We would probably initially tune these algorithms to only give this confidence score, a positive confidence score, for the highest degree confidence scores. And even though, so if it doesn't give a positive result, doesn't necessarily mean it's not same source, but this might be a way of speeding up the process, because we now no longer need a second examiner to come in and provide a verification, because we have confidence that the algorithm is right, the examiner is right, and they're being done in parallel or separate from one another. And since we have congruence, we can report that conclusion. Well, so what would we do if the algorithm doesn't agree, especially if we're thresholding it to only provide the highest confidence scores? So here we have a workflow where same source, the examiner reaches same source, the confidence score does not agree. Well, then we could just do what's traditionally done today, day in and day out. You involve a second human verifier and see if that second human agrees with the original examiner. And if they do agree, then you report the result just as you do today in casework. One thing should be mentioned, I think it's critically important that examiners are able to interpret any kind of confidence score that is produced. These results need to be interpretable, and one way of doing that would be to see what features the algorithm is using and how the algorithm is aligning the two samples. So here's an example of two heat maps where the features have been highlighted, and the examiner can take a look at that and say, yes, I agree, those are useful features. Or they might say, for example, nope, I think those are subclass features. I don't agree. I don't think this is a reliable result. And they can then choose to disagree with the algorithm's result. Closing thoughts, I think it needs to be said, I think it's fairly obvious, but it's worth stating that the acquisition and visualization components of what I've talked about require validation and of course require training prior to being implemented into a laboratory. And of course, use of algorithm is also going to require additional validation. And invariably, when this first gets used in criminal casework, that's going to require courtroom admissibility and pass that threshold as well. That being said, I don't think those are reasons to not adopt this technology and for the profession to move forward because it has such great potential. You know, the integrated comparison notes and documentations has the ability to really potentially streamline things and improve examiner accuracy and quality. The streamlined analysis with instant recall of virtual specimens has its clear advantages, and that's provided greater insight into examiners' decisions and has potential to expand our profession's shared pool of knowledge by being able to share examples, share training samples with one another digitally rather than relying on just the physical specimens. And finally, ultimately, I hope that we can get to a point where we can support conclusions with understandable and explainable comparison algorithms. Thank you for your time and listening. If you have any questions, there's my email address. I look forward to answering any questions in the live panel. Thank you.
Great presentation, Todd. Thank you. Our final presenter for the day is Johannes Soons, mechanical engineer with NIST. Hans will discuss the strengths and limitations of computer-aided methods and their implementation into casework workflow. Hans is a mechanical engineer in the Surface and Interface Metrology Group of the Physical Measurement Laboratory at NIST. He also leads the Forensic Firearm and Toolmark Analysis Project at NIST. Hans received his PhD at the Precision Engineering Laboratory of the Eindhoven University of Technology in the Netherlands. Since 1994, he has been employed at NIST as a researcher, group leader, and project leader working on surface texture metrology, precision machining, measurement of precision optics, and forensics. Hans' current research focuses on improving methods for objective firearm and toolmark analysis and addresses measurement methods, standards, databases, similarity metrics, algorithms, and weight of evidence. With that introduction, here's Hans.
Good afternoon. My name is Hans Soons, and I'm a mechanical engineer at the National Institute of Standards and Technology. In this presentation, I would like to give you a high-level overview of computational techniques for firearm and toolmark analysis. I purposely use the term computer-aided in the title instead of computer-based, as these techniques are being developed to assist the examiners. First, before I get going, a few disclaimers. Any mention of products in this presentation does not imply endorsement or that they are the best for the purpose. Furthermore, any opinions expressed in these presentations are my opinions and not necessarily those of NIST. As you know, a key step in firearm and toolmark identification is the comparison of so-called individualizing marks left by the firearm or the tool. This is typically done using a comparison microscope, and the examiner has to assess whether the similarity between marks exceeds the best agreement demonstrated by marks from different tools, and whether the similarity is consistent with the agreement demonstrated by marks from the same tool. This process is currently subjective and relies on the skill and expertise of the examiner. As with other types of pattern evidence, this current practice is under scrutiny, and examples of that scrutiny are, of course, the 2009 report by the National Academies, as well as the 2016 PCAST report. And although well-meaning people may disagree on some of the findings in these reports, there seems to be a consensus on two key issues. First of all, the need to move from subjective comparison methods and criteria to more objective methods. And secondly, the need for statistically sound measures that characterize the reliability or evidentiary strength of the comparison result. Addressing these concerns, however, is difficult. First, there is a significant variability in marks produced by the same firearm, even when shooting one cartridge after the other using the same ammunition. On the other hand, there can be similarity in marks produced by different firearms. What keeps examiners awake, for example, is the possibility of different firearms leaving very similar marks because they were manufactured using the same tool. And this is why firearm manufacturing processes are a key part of examiner training. The manufacturing method of a firearm furthermore affects the characteristics of the individualizing features. Although we know that we have to look for scratches, peaks, and valleys in surface topography when trying to determine whether two cartridge cases or two bullets were fired from the same firearm, the nature of the individualizing features is not as well defined as, say, minutiae in fingerprints, where we kind of know what to look for. Finally, there is no consensus on objective comparison metrics, and it's very difficult or a lot of work to obtain the large amount of comparisons required to estimate error rates or any other measures of reliability. So what is being done to address these challenges? First of all, there is an improvement in the quality of toolmark data by measuring the actual topography of the samples instead of relying on reflectance microscopy images that are significantly affected by reflectivity, focus, and lighting conditions. This also enables examiners to measure samples only once and then use the topography data to perform virtual microscopy comparisons on the computer in a manner similar to traditional comparison microscopy. And this process is called virtual comparison microscopy. Secondly, there is the development of comparison algorithms that yield an objective toolmark comparison score with some measure of its statistical significance, such as an applicable error rate or a likelihood ratio. A recently published standard for topography comparison software considers three categories of comparison software. Category 0 algorithms generate a ranking score typically using a proprietary algorithm. These algorithms are used for database searching, typically during the investigative phase. And the result of such a search is a list of samples in the database that are ranked according to toolmark similarity with the submitted sample, similar to when you do a web search. So typically these algorithms do not make a call whether it's a match or not. They simply rank according to similarity. Because the nature of the score is proprietary, the score should not be mentioned in reports, at least in reports that are being used during in court procedures. However, the search rank of the data in the database search can be reported, although you cannot attach any statistical significance to how high the sample ranked in the search. Whereas category 0 algorithms have a score that is not published, that is proprietary. In the case of category 1 algorithms, the examiner is able to describe the principle of the score. And in that case, the score and implied degree of similarity can be reported, but you cannot attach some kind of confidence metric to your result. For that, you need category 2 algorithms that can report some measure of reliability, such as an error rate or a likelihood ratio, based on citable studies that have to be relevant to the compared specimens. And that is obviously where we want to go. In the second part of this presentation, I would like to give you an overview of the various steps in a comparison algorithm, ranging from data exchange to classification. I'm not going to talk much about the characterization of uncertainty or evidentiary strength, as that will be addressed in Alan Zhang's presentation later on. The first step is the transfer of topography measurement data. Currently, the ISO X3P data format that was developed for exchanging topography data is becoming the preferred data format for exchanging topography measurement data of Toolmarks. But the X3P format was developed by ISO for a host of different applications. It's a generic format. It doesn't know about forensics. And that's why the OpenFMC group is currently developing an extension to the X3P data format. And the extension describes metadata, that is data about the data, that is relevant for toolmark analysis. And examples of that is some information about the case, some information about the firearm, some information about the ammunition, the region of interest that is being captured, etc. And OpenFMC, by the way, is a group of researchers, examiners, as well as instrument manufacturers that are working on means to make data transfer as smooth as possible. Once we have the data in the computer, a critical step in comparisons is something called image segmentation. This means that we divide the image up into regions of interest that will be compared separately. Examples of a region of interest are the land engraved area on the bullet or a breech face impression on a cartridge case. This step is critical because some regions on the sample, such as the primer roll-off, are not informative, but may significantly affect similarity results if they are compared. Furthermore, different mark types, such as striation marks and impressed marks, require different analysis methods. And finally, the relative location of different marks, such as the ejector mark and the firing pin impression and the breech face impression, the different location between these marks may not repeat over firings, and therefore you cannot analyze them as one image, but you have to compare images focused on that each address these individual marks, like the ejector mark or the firing pin impression. Now, to illustrate some of these concepts, I'm presenting here an example of a topography measurement of a land engraved area on a bullet. The measurement data is presented in false color. The yellow areas are high, present peaks, and the blue areas present valleys. The white areas are areas where no measurement data was obtained, for example, because the slope was too high or because there was dirt on the surface. For a striated mark such as a land engraved area, we are basically interested in the surface topography profile in a plane orthogonal to the striae. And we obtain that profile in the following manner. Here we see at the top the same data, but I've rotated it 90 degrees. And the first step is to apply an edge detection algorithm that identifies strong striae. And those strong striae are here shown in black. We then use those striae to rotate the image such that the striae are vertical. And you see that here in the top image. And now the striations are approximately vertical. We then average the surface heights in each pixel column for those areas that have strong striations. And that yields at the bottom the cross-section profile that we then further process by removing the shoulders at the left and right of the image. In some cases, there may be significant deformation of the striations. And in that case, we apply an algorithm that basically corrects for this distortion of the striations so that the cross-section profile can be accurately determined. After performing this these steps on two bullets, in this case fired from the same firearm, we end up with two profiles of the land engraved area. For an algorithm, these profiles look very similar. As an examiner, however, you know that the overall circular shape of these profiles is at best a class characteristic, but is not individualizing. What we need to do is we need to compare the smaller wriggles that are superimposed on that circular shape. Those contain the individualizing marks. And in this context, it's useful to consider a measure profile or topography data in general as consisting of several components. These components range from the overall shape or form, which is characterized by very large wavelengths, in this case the overall circular form, to noise with very short spatial wavelengths. Repeatable individualizing marks are often found in the so-called roughness region, which is characterized by small to mid-spatial wavelengths. And to extract these, we apply a so-called bandpass filter to the measured profile that attenuates noise, form, and waviness, and that highlights this roughness profile. And here you see the result for our two land engraved area measurements, bullet A and bullet B. And you can see several features that in this case look like individualizing marks. Now for a human, it's almost impossible to look at these profiles without identifying several similar features in these profiles. For an algorithm, this is not so obvious because the similar features do not occur in the same position. So the next step is typically a step what we call registration, where one of the images or profiles is moved to maximize the similarity between the two profiles. And here you see that being done in an illustrative way. So now the various peaks and valleys line up. And this registration process typically is performed in such a way that the similarity between the two profiles or images is maximized. And that brings me to, okay, how do we describe similarity? What are objective similarity metrics? One method is based on the identification and comparisons of features, which is very similar to the way that minutiae in fingerprints are being analyzed. In this case, the algorithm would first evaluate the surface topography data of each surface that will be compared, and it identifies features. And the features that we're looking for are typically peaks and valleys with a very distinct lateral position. If you do that for both surfaces, in this case, as an example, for two breech face impressions, the next step is to rotate and translate one of the samples to maximize the number or ratio of similar features that are in the same position. In other words, we want to find the number or ratio of similar features where the difference in location can be explained by a realistic rotation and translation of the compared surface. And the advantage of this method is that once the features are identified, the evaluation of this number or ratio of similar features can be done extremely fast. So these algorithms are often very well suited for database searches. They also very much mimic what a human would do when comparing two samples. The second basic approach to similarity is not to bother with features, but simply evaluating the similarity, the height variations of the profiles or images at every measured point after the images have been registered. There are various similarity metrics that you can apply. For example, the mean absolute difference, the root mean square difference of surface heights. But currently the most popular metric is the correlation coefficient. This metric has a value of 1 if both surfaces or profiles are the same, except maybe for a vertical scaling factor, and a value of -1 if both surfaces or profiles are mirror copies of each other. The metric equals 0 if there is no correlation between the height variation of the two surfaces. So let's try this out for a comparison of the breech face impression on two cartridge cases that were fired from the same firearm. Here you see again a false color plot of the height measurement data, and again yellow indicates peaks and blue indicates valleys. The hole in the center is the firing pin impression where we obtained no measurements. Our first step is to trim the data to obtain the region of interest, again in this case the breech face impression, and then we apply a bandpass filter to highlight the individualizing features, after which we register the two images, we rotate or translate one of the images so that the correlation coefficient between the two images is maximized. And in this case, you can see actually quite a few similarities in both the granular as well as the striated features on the breech face impression. The correlation coefficient that was calculated was 63.9%, which is actually a pretty high number. However, by itself, a score like this is meaningless. We need context. How does the score compare to scores obtained for if we fire the same firearm again and again, so known matching samples, as well as how does it compare to the score obtained when comparing non-matching samples fired from the same or similar firearms. And to do this, to provide this context, we have to perform many comparisons. And here you see a result of a small set of comparisons. On the horizontal axis, we see the score, the correlation coefficient in this case, and on the vertical axis, how often it occurs. The red bars are comparisons of cartridge cases fired from the same firearm, and the blue bars are for cartridge cases fired from different firearms. And we see that our similarity score that we obtained of 63.9% is consistent with scores obtained for known matching comparisons and significantly higher than that of known non-matching comparisons. Now, in principle, when you have data like this, you can draw a threshold line between the two distributions and classify a comparison result as a match if the similarity score exceeds the threshold value, and say an inconclusive, conclusive, or exclusion if it is below the threshold value. However, in this case, because the two distributions are pretty close together, we would expect in the long run some false positives and some false negatives, and it's important to evaluate those. To improve the separation between the two distributions, John Sung at NIST developed the so-called congruent matching cells method. And this method addresses some of the challenges of area-based comparison methods, in particular, the possible presence of areas with poor mark reproduction. In this method, which is somewhat between the feature-based methods and aerial methods, one of the surfaces is divided into cells, the reference surface on the left-hand side, and then each cell is allowed to roam the compared surface to find the location where the similarity is the highest. And here you see the result of two same source sample comparisons. And although the location of the cells on the compared surface is not the same as that on the reference surface, you can explain the difference by a rotation of the compared surface. If you perform the same comparisons for two samples fired from different firearms, which you see here at the bottom, then cells may find a location on the compared surface that have high similarity, but the location of the cells cannot be explained by a rotation or translation of a sample. It doesn't make sense. So the similarity metric for this method is the number of cell pairs that have both a high similarity and a congruent registration position. When we apply this method to the same set of comparisons that was shown previously, we see now a larger separation between the known matching and the known non-matching score distributions. When we applied this method to more extensive data sets, we were starting to see some overlap between matching scores in red and non-matching scores in blue. However, one of the advantages of this method is that the non-matching scores are consistently low, and that holds promise for low false positive error rates. We've discussed several comparison scores, and of course the question then becomes which kind of score should you choose? Now, in practice, you may not have to choose. In practice, it may be beneficial to combine different kinds of scores. And of course, in practice, you almost always combine results from comparisons of different regions of interest, like the firing pin impression and breech face impression. Now, to clarify this concept, I'm showing here some simulated data where each dot represents a comparison. And on the horizontal axis, we have one comparison score, say the correlation coefficient, and on the vertical axis we have a different comparison score, say the number of congruent matching cells. Now, by itself, each score has some overlap between matching and non-matching scores. However, if we combine the two scores, as shown here, there is now a significant gap in the distribution of the combined matching and non-matching scores. So using two scores or more scores can sometimes provide benefit. Now, the classification of scores into a declared match or a declared non-match has the advantage of a very clear outcome. However, there is a major disadvantage, and that is that the message to the jury is going to be very different for scores slightly to the left or slightly to the right of the threshold value. Furthermore, all comparison scores with a score above the threshold value yield the same conclusion, whether they are close to the threshold values or very high, say 100% in this case. So a subject of much research is to forgo classification and instead present the strength of the evidence. One approach that will be discussed later is a likelihood ratio, basically the ratio of the likelihood of obtaining the comparison score if the samples were fired from the same firearm versus the likelihood of obtaining the comparison score if the samples were fired from different firearms. So in this case, we do not provide the jury with a conclusion, but rather the strength of the evidence for each scenario, or the ratio of the strengths of the evidence for each scenario. So that brings me to the end of this high-level overview. I've discussed several workflow items in computer-aided comparisons, ranging from data exchange to image segmentation to classification. So where are we in terms of implementation in actual casework? For the last 2 decades, algorithms have been used for database search during the investigative phase. However, these algorithms only provide a ranked list of possible matches. They don't make a call, they simply rank according to similarity, which is very similar to a web search. Virtual comparison microscopy is currently being introduced in court. And here, algorithms have a relatively small supportive role in improving feature visibility, highlighting similar areas, possibly fast assisted registration, etc. But their role is relatively minor. Algorithms for objective identification and characterization of evidentiary strengths, which is something that's very difficult to do, both for humans as well as algorithms, those are still a few years out. So what are the key challenges? Firstly, there is currently no consensus on the best scoring metrics or processing parameters. It's difficult to translate to human expertise and skill into algorithms, especially regarding the identification of subclass characteristics. Differences in firearm characteristics and ammunition can have a major effect on comparison score distributions and therefore on estimations of the strengths of the evidence. And of course, the characterization of the strengths of the evidence, how do you estimate it, how do you express it, is still a major challenge. On the other hand, there are significant and promising research efforts. Results are finding their way in commercial products. Virtual comparison microscopy is being introduced in courts. As I mentioned at the top of this presentation, these various techniques are expected to help the examiner, for example, by providing a second opinion or by providing estimates for the strengths of the evidence, estimates that have a well-grounded, that are statistically well-grounded. But of course, the application of these algorithmic techniques will require careful consideration to avoid confirmation bias. And with that, I would like to thank you for your attention. And if there are any questions, I would be happy to answer those.
Thank you, Hans. This is Robert Thompson, the moderator, and we're going to start our Q&A session. First, I'd like to thank the presenters, and then also like to thank the attendees virtually sending in questions for this and hopefully other discussions for the next few days this week. So I'm going to start out, and each of you might have touched base with this question, but it's kind of like the big elephant in the room. A lot of people ask this question of me and probably you. Do you expect in the future that this research and objective or automated methods will eliminate the human expert in firearm and toolmark examinations? So anyone can jump in.
I think Hans spoke to that in his presentation. No, I don't see that happening. I see perhaps even a greater role for examiners to provide the interpretation and meaning of the results. So no, there's still examiners that need to interpret the results and provide expert testimony and interpretation to what those results mean for each given case.
Yeah, I agree with Todd. I think there are several reasons why I think for the foreseeable future, the role of algorithms will be kind of as a second opinion. First of all, humans are extremely good at comparing patterns and evaluating whether or not something is significant. It's very difficult to teach an algorithm about subclass characteristics. That requires a certain manufacturing expertise and background knowledge about the samples. Humans are good at seeing when something unusual occurs, and an algorithm may not be able to do that. And Robert, as you like to say, at the end of the day, somebody has to testify. And it's sometimes difficult to get a computer to do that.
Brian, do you have any thoughts?
They pretty much covered it, but so I would agree with them, at least for, not for a really, really long time. I mean, nobody knows what's going to happen 100 years from now, obviously, but not for a really long time. I would say that these new microscopes and the analysis techniques, they're just an additional tool for the examiner to use in their toolbox. And so it's an additional thing that they can use to verify the source of fired bullets or cartridge casings.
So Todd, here's a question also for you, probably best. And this gets into as an examiner, and you had case flow. What might be the issues is when you're using archived digital evidence for initial comparisons, do you think it'll still be necessary to acquire the physical evidence and view the specimens side by side via traditional light comparisons as a form of confirmation? So basically, I think this is a question is, if there's needs to be confirmation or maybe another call from another agency, do you think ultimately at the end there's still going to be necessary a physical comparison?
Not necessarily. And, because, for example, we digitize evidence a lot in other disciplines, whether it's friction ridge analysis. Now, many latent prints are digitized and scanned and compared on computer screens. We digitize chemical fingerprints, right, through either FTIR or GCMS. We digitize DNA profiles, and we accept those DNA profiles. So I think that comes down to kind of a risk assessment for the laboratory and their confidence that the scan represented is the actual physical specimen. Of course, if there becomes any doubt to that, you need to retain the physical specimen. But as long as the things that Brian and Hans talked about, you have confidence that the measurements accurately represent the geometric surfaces that you're seeing, those virtual representations can be used for final conclusions. And you have confidence that item 1 is indeed item 1 from the crime scene and so on.
So there's another question came in, and it's similar to what's going on in the lab. So this is for Todd also. It's mentioned that the VCM is being used in casework. Which microscopes are most often common in the labs for the VCM? I know it's still early in the technology being accepted in a lot of the laboratories, but can you think of the types, maybe not the brand types, but the types of technology are being used?
Well, I think all three of us could probably speak to that. I think the two I see the most are photometric stereo and the focus variation. That's then, Thomas provided some outlines of that technology, but it's still to be determined what, I think each has the strengths and the weaknesses.
And this is maybe for Brian. Can VCM be connected to the IBIS technology or any of the other, I would say, investigative database search systems?
So is that like the NIBIN systems?
Yes, yeah.
Okay, so I'm assuming that's the 3D VCM systems that you're talking about, connecting to the old NIBIN systems, which are based on 2D microscopy. It's possible, I think. I think there's been some work investigating this, whether you can convert, well, in one direction, you can convert 3D topography into virtual images. Okay, so you could go that way. Going the other way is a lot more difficult. So taking a 2D image where you don't know much about the lighting orientation or the illumination intensity or aspects of that, or the materials involved, converting that into a 3D image would be a lot more difficult. So it may be backwards compatible, where you can take new images from a VCM system and possibly compare to older systems. But again, if you don't know much about the lighting conditions, then it may be a little challenging. You would probably have to play with the virtual lighting in the VCM system to try to find, a comparison or a match. So it might be possible, but there would be some challenges involved.
And I think, like, if whatever technology can produce virtual images, it seems to be a simple step to be able to do the virtual comparisons using that technology, just to adapt it.
Yeah, to some extent. So the more modern systems within the NIBIN systems do measure 3D images, and virtual comparison of those 3D images is the process that's being used to get from a ranked list to a much smaller set of possible candidates.
So Hans, since I have you, what quality controls are in place to identify or check for an image flip? We were talking about that during the other standard, that they're still discussing the flip. How can the 3D scans include a visual orientation reference to help resolve or mitigate this issue? Or should it be, is there some kind of a clue that could be just to give the examiner confidence that it's not a flip?
Yeah, so to give you some background, so the X3P standard has been around for a few years, and there was some ambiguity as to what the order of the data was in the data file. And that has resulted in some software producing this image flip. And that's a very bad thing for forensics, because if you flip or mirror the image in Y direction, then you cannot make that image match anymore with an image saved the same that wasn't flipped. There is no rotation or translation that you can make to make those images match. So ISO has recognized the problem of possible image flip, so they made an amendment to the standard that clarifies exactly how the data should be organized, and they updated the revision number. So now we know that if we get a file with an updated revision number, then there's really no excuse anymore for an image flip. And I expect that software that doesn't adhere will make an effort to adhere to that new standard. So in summary, if you're using images from older systems, always check whether image flip is present at least once. If it's from newer systems for XRP files that have this new revision number, then there shouldn't be any image flip anymore.
So Brian, just your opinion on how often do 3D topography instruments need to be calibrated and checked to ensure that they're functioning properly? And I'm guessing this would be in, not necessarily in the NIST world, but what you project perhaps would be in a crime laboratory.
Yeah, that's a tough question. I tried to go into that a little bit in the presentation, and it's definitely not going to be a one-size-fits-all solution, because there are so many factors involved. There's the kinds and number of instruments that you have, the number of operators. How often do you do casework? You know, is it every day, or is it maybe a couple of times a week, or something like that? And the type of instruments that you have. So there's so many factors that are going to determine the frequency of which you're going to need to do calibrations. I would say that you're going to need to do checks, right? And especially control charts. I think there's got to be checks done probably every single day that you do casework. There's got to be some kind of check has to be done, so that these numbers can be tracked over time, and you can see, are there any variabilities? Are there any trends? Is something going out of spec? You'll be able to see that very quickly if you're doing checks. Now, you're probably not going to have to calibrate the instrument in every single manner every single day, right? But again, it's going to vary quite a bit. And the organizations that I mentioned, they are going to hopefully be helping the examiners find the answers to these questions, so that they're not on their own with this, right? They're going to be doing a lot of the legwork and helping out with that. I'd say when you get started doing measurements, 3D measurements, the best thing to do is just do a lot of calibrations, a lot of checks, and keep track of the control charts from day to day, and you see how much the values are varying, and that gives you a sense of confidence in your system and your operators, how much is going to vary. And once you're comfortable with it and you see that it's, maybe it's very stable for a while, then okay, maybe that means that you can reduce the amount of calibrations that you need to do, maybe once a week. Honestly, I don't know exactly what the answer is going to be, and it's going to be dependent on every single laboratory, I think. Just so many variables to determine.
This is for Hans. What is the endpoint with the likelihood ratio research? I'm just reading it directly. Will examiners in the future hopefully be able to apply a statistic in court? How developed is this research so far? I'm guessing an estimate as to when you start seeing it in perhaps trials.
It's going to be a few years out, and we've been saying that for a few years. So this is a very, very difficult problem. And if you're interested in what the future may look like, there's a presentation by Alan Zhang on Thursday on the so-called rapid fit thing that goes in more detail about how do you characterize evidentiary strength. And it may end up as a likelihood ratio, which is very popular in Europe. It may end up as something else. We don't know at this stage. But it's a very hard problem because, for example, if you firearms that are manufactured in a different way or different types of ammunition have a big effect on these similarity distributions that I was talking about. And somehow in the estimate of the strength of the evidence, it has to capture that. If a cartridge case doesn't mark well, then these likelihood ratios or error rates are going to change.
So I'm going to give this one to Todd because he's rather busy with evidentiary hearings himself, and not only his casework too. Are there any current cases that you know of that's undergoing Daubert review or maybe any evidentiary review of VCM in the United States? Is it VCM accepted in the courts of any other countries yet?
Well, that's an easy one to answer because I'm not aware of any.
Okay. That was great. not a search for another question. So, I know there's one for Hans. Have studies, and I think you did give a little bit of this in the presentation, have studies been conducted to demonstrate how the inclusion of the entire sample surface, as opposed to only the region of interest, can affect the similarity scores?
Not that I am aware of, except that we know that this segmentation process where you divide up your measured region into smaller regions of interest is extremely important. If it's not done right, then these distributions change and you may get more overlap. And there are several reasons for that. For example, if you were to include, if you do a primer measurement and you include the roll-off of the primer, now from a physical point of view, you don't expect firearm tool marks to be on that roll-off area. But you can have pre-fire marks that look very similar. So by including that roll-off, you make it harder for the system to find the correct solution. Another example is aperture shear versus breech face impression. The aperture shear mark, in that case, you're interested in the cross-section of the profile of the aperture shear mark. If the aperture shear mark, if you look at it from the top and it's like deformed, that's not necessarily a sign that, and it differs from one that's straight, that's not necessarily an exclusion because you're really interested in that cross-section. Whereas for an impression mark, you analyze the whole surface. So, and another issue is that the relative position and orientation of, say, the firing pin relative to the breech face mark or the ejector mark may not be repeatable from shot to shot. And if you analyze that one complete image and you don't analyze them separately, at least for an algorithm, you may get at the wrong conclusion. So image segmentation is very important.
So Todd, this is for you. Previous VCM information has suggested difficulty in acquiring firing pin or chamber marks due to the curved surface. Is this still the case, or are there now areas that can be compared like aperture shear? And I think we've already answered yes for aperture shear.
Well, I think there's a reason why you see the lion's share of the preliminary work focusing on surfaces like breech faces and bullet lands, because those are the easiest to image, measure, and compare. And that, I think that's the same whether under the light comparison microscope or under measuring them using one of these 3D measurement microscopes. So I like the analogy, DNA analysis didn't start with 3-person degraded mixtures. It started with single source and 2-person party mixtures, right? You have to prove the concept first, make sure it works, and then you can move on to the more difficult samples. So with that said, whether you're viewing chamber marks or firing pin impressions under a light microscope, that's more difficult. I've done techniques like make my own light reflectors or light diffusers to help illuminate those surfaces. And so it is more challenging with these microscopes to measure those surfaces. I've seen recent research that is now starting to tackle that. And so if you look at the literature, for example, at NIST, they've applied what's called, rather than CMC, they're developing a method called CMX, congruent matching cross sections, because it requires a different technique to compare. So what we'll continue, I think it's just an engineering problem and a different approach, but it's going to be solved. And we'll see more and more coming out in the research realm with regards to those different surfaces.
So I want to try to squeeze in one more. Someone mentioned that it's difficult to get management in a laboratory to assist in research and development. And how are there ways you can support a request if you do need to do that? Let me answer that first, is that I think there's going to be, if you get into the realm of 3D, like virtual comparisons and later on statistical based measurement of similarity, you're going to be doing research in that you're going to be validating that system inside your own laboratory. So, of course, my phone would ring just as purposely now. So that's where I see it, is that is going to be research and development, mainly because you necessarily have to do that in your own laboratory when you get into the system. Go ahead. Any of the other presenters, go ahead on this one.
Sorry, Rob. Right, I kind of missed the actual question.
Okay, the question is, it is difficult to convince management to invest in research and development for Firearm and Toolmarks. How can we support our request? And my point is, you're going to be doing research and development during your validation phase for sure. Just get involved in this new technology.
Yeah, I think it's a good point, and all lab managers certainly want something that's turnkey, right? But I think we're seeing a maturation or maturing of the technology to the point where laboratories are adopting it, and you no longer have to be at the tip of the spear. For example, agencies like the FBI have adopted these instruments, are using it in casework, so you don't have to be the first one out the door. And I've tried to provide some of those use case scenarios that I think do present key advantages of the technology. For example, doing all the note taking right there in the same pane, and all those notes get incorporated, tied to the physical samples, and then get exported as an entire note package at the end of your examination process. So things like that. I only had 25 minutes. I had to go really, really fast. I could probably spend a couple hours showing all those different features. So I would say look into the technology, talk to the different vendors, get some demonstrations, and see if the technology fits you, and maybe you can come up with use cases that I haven't even thought of.
I think we've gotten to the end of our Q&A. Thanks for the presenters. Virtual claps for everyone.